Hello there, welcome. Alright, finding the orthocenter of a triangle. That's going to be the focus of this video. We will come back here to this adjustable triangle in just a moment, and I'll do two different problems using algebra to find the orthocenter. But first I'd like to do a little visit here to something I constructed where the result was the Euler segment. And that particular segment is in blue right here. And the three triangle centers that are on the Euler segment are the circumcenter, which is the intersection of perpendicular bisectors. And the other endpoint is the orthocenter. That's the one we're going to be solving for shortly. And where are they? The altitudes give us the point of concurrency called the orthocenter. And the centroid is where the medians intersect. And without getting into too much detail, you can pause this and read more about the Euler segment if you'd like, or you can send me a message if you have any other questions about it. But there's a nice little property that always occurs if I were to drag the vertices or one of the vertices in order to get a right triangle, which I am just now completing. What I wanted you to see is that the orthocenter will always be on the 90 degree vertex if the triangle is a right triangle, and the circumcenter will always be on the midpoint of the hypotenuse. And the same thing would occur if I created angle K to be 90. So that should help. If you're given a right triangle, it should be pretty easy to find the orthocenter. It's the vertex where the 90 degree angle is. But let's look at an acute and an obtuse triangle, and we'll go through these steps for finding the intersection of altitudes for this triangle, where we will first find slopes of two sides, and then we'll find the equations of the altitudes to those two sides, and then we'll solve the system of those linear equations. And this first problem, this is our acute triangle. And one of the nice things about this, if you notice that two of my vertices have the same y value, that makes it easy to find the slope. That's a horizontal slope. And it also makes it easy to find the equation of this line. If I wanted the equation of this line, it would be simply y equals -2. But what I'm interested in is constructing this perpendicular. The x value is constant, so I can say that the equation of this altitude is simply x equals 11. Okay, so let me clear this ink. And I'll show you again. These are the two red altitudes whose equations I'll be finding. This one, because it's vertical, has a pretty straightforward equation. It's x equals 11. So these two steps I've done already for this altitude. Let's do the procedure for finding this equation of this altitude right here. So let's hide these. And what I'm going to do first is find the slope of this side. And then I'll find the perpendicular slope, which goes through this point. So here's my slope formula: y2 minus y1. 9 minus -2 over x2 minus x1. 11 minus 17. Alright, 11 over -6. And now the process for finding the equation of the altitude involves understanding that altitudes are always perpendicular to the base. So we just figured out that the base at the moment, which is side CA, has a slope of 11 over -6. So the perpendicular slope means that we take this fraction and we flip it, or we get its reciprocal, and we also change the sign. So positive 6 over 11 will be the slope of the altitude. So for finding the equation of the altitude, I'm going to start with point slope form. The slope of my altitude is 6 over 11. And now I need to substitute in for x1 and y1 in this point slope form of a linear equation. And the only point that I know of on this altitude is point B. So that's the way this works. When we find the slope of this side, I take the opposite reciprocal to get the slope of the altitude. And then I also take the coordinates of this opposite vertex from the base where I started, and I plug these in for x1 right here, which is 0 for point B, and y1, which is -2. So this becomes y plus 2. Here's the equation of this altitude, which is now in slope-intercept form. And if you'll remember, the first thing I solved for was the equation of this altitude, which was a vertical line going through x value 11. So this is my second altitude equation. What I'm going to do is clear this ink and put the real constructions up. Here we have them. These red lines are the two altitudes, which will give me the intersection of the orthocenter. And now it's just simple solving of a system of equations. So since this is x equals 11, I'm going to use substitution, and I'm going to put 11 in for x. And now let's simplify. I get 6 minus 2, so I get y equals 4. And this does seem to match up with the graph, which I don't need to do this, but I think it's helpful to see a picture of the graph while we're solving it. So now, as I'm finding the coordinates for this orthocenter, I've just solved for the y value of 4. And if we use deductive reasoning, we can say that because this vertical line always has an x value 11, the orthocenter also has to have an x value of 11. So there is our orthocenter 11, 4.